Circles. So this is 10-1. I forgot to put that on there. It's just circles. So let's define a few parts of the circle, things that you already know, and just putting it down on paper, because as we go throughout this chapter, a lot of the terminology just gets reused. So you have to know what things mean in order to, use formulas and theorems, stuff like that as we get into it. For example, what is a circle? Can't use the name, can't use the word to define the word. It's a round. Yes, sir.
Has no sides.
Has no sides, okay. How do you know a sideless shape?
There's curves.
Curves? All right, well, let's do this. A circle, let's just do this first. Circle is it's a set of points that are equidistant to a center. Actually, they call that the same point, but we'll just call that the center. So what that means is that every point that lies on a circle, in order for it to create that circle, they're all the same distance from that center point. The distance from the center point to the edge of the circle is called a what? The radius, yeah. And that's where the terms that you guys already know come into play. You just didn't realize that that circle is just a bunch of points that are the same distance from the center. That's all that means. Okay. So as you go through this, a radius is the distance. What's up? We're not done with that? Sorry. So that radius is the distance from the center to the circle. Do you want us to call it the side, or do you just want to call it the circle? The edge? The circle, yeah, that's what I figured. So the radius, and obviously you've seen this before, that radius is the lowercase r.
Are we going to read that book?
What book?
Kate, Queen died, and the solid's name's Radius. You know it?
No.
I love that book.
No, I've never heard it.
It's like it's like medieval times, and they like compare like people to like the things in the circle.
No, I've
It's
never.
like that's how I remember it.
I've never heard of that. What is? Yeah, what is it? Later on, we should finish up with a little bit of time here.
Yeah.
Google that and email me that. I'd like to know what that. I've never heard of
It's
that.
an awesome book.
I've never heard of
It's
that.
like how I learned it.
Okay, I've never heard of that. So when we finish up here, find it and email it to me. I'd like to see what that is. Okay. The next thing is called a chord. You guys actually know what that is. Hannah, put away your phone, please. Thank you. Like, put it away. You don't need it next to you. There's nothing that important in the world right now that you need to see. Have your phone out. That's the other thing. Stay off your damn phones. Plain and simple. It's getting old. It's getting really, really old. Another reason why we can't keep our eyes on the board and learn what we're doing, because we're too worried about all this Snapchat old stuff or whatever you guys are doing with the Twitter or whatever. It's annoying. Teachers are getting really fed up with it. Just so you know. Once again, you're choosing your own destiny here, guys. Chord. A chord is a segment that's in a circle that has endpoints on the circle. No. Morning. So a chord. A chord is a segment in a circle that has endpoints on it. So a segment with endpoints on a circle. I'm going to get really lazy here real fast because the word circle is too many letters for me. And I'm going to start abbreviating it with a symbol. A symbol. Sir. We use that a lot of times you'll see that written because circles are always going to be defined by the point that's in the center. So it'll say like circle A. That just means the center is point A. That's all. Okay. And as we get into this, you'll start to see that more and more. What's the diameter?
Radius. Yeah, okay, center.
Across the
Other side.
middle, across the center.
It's just half the radius. Two radius.
But here's the thing: if it's two radius, if you're saying it's two radius, well, here's one radius, here's another radius. Is that a diameter?
It's like splits in the middle of the.
One end to the other end?
Yeah, it's you guys are all kind of on. You can physically draw one, and you're all right on the same basic principle here. The diameter is just it splits the circle in half. It goes through the middle. It goes through. We call the middle the center. Sorry, I forgot where it was. So the diameter is a chord that goes through the center. So technically a diameter is a chord. Okay? It's the longest segment that you could put in a circle because everything else becomes shorter as it gets to the edges. All right? So the diameter is a fancy chord through the center. And like you guys said, is your phone going off again?
Yeah.
Turn it off. Just shut it off when you come into class. I mean, seriously. The diameter is equal to 2 times the radius. You know, that's what you were saying. You double the radius, you get the diameter. Or cut the diameter in half, you get a radius. It works going either way. Okay? It works going either way. The next two are ones that are new. Up to this point, this is stuff that you guys have all seen. You may not have heard the word chord before as far as the circle is concerned. They probably don't get that fancy, but these last two are the more fancier ones. What's called the secant and a tangent. Now, secant and tangent are also terms for trigonometry. They're a little bit different in this case here, okay? They're completely different. A secant is a line through a circle. So a secant, let me make sure you've done. A secant is a line that goes through a circle. It's a line that has it touches the circle at 2 spots. Okay? It's a line that touches the circle at 2 spots. We bring up this whole idea of what's called a secant now, just so you get the definition of it, because we actually there's a section, what is it? It's 10.4, I want to say, is all about what happens with the secants as they intercept arcs and things like that. And then the last one that we'll talk about is what's called a tangent. Let's see here. You know when you say that you're going off on a tangent? You know how that terminology means you're going off on, you're switching directions, you're going off on something else? When you say that you're going off on a tangent, it means that you have stopped what you're doing and changed directions. You made it to some point in a conversation and you switched and went somewhere else. Do you guys agree with me on that? It's kind of the lingo of it. You're like, hey, look, a duck. that kind of whole thing. All right. So when you think of tangent, a tangent, when it comes to a circle, is anything that touches the circle at one spot. So if you go off on something else, you're changing directions, you change the point, you change what you're talking about, there's one thing that changes. So a tangent is, it just changes direction. So it touches the circle at one spot. And I guess the only other thing that you can think of that kind of makes sense is that if you touch a circle at just one spot, so let me draw this. If you touch a circle at one spot, you create a right angle with a radius. So if you create a right angle with a radius, what does that look like as you bring it around? Looks like a letter T, doesn't it? That's why they use that. That's where the terminology comes from. Yeah, I'm kind of stretching it a little bit here, but trying to think of an easy way for you guys to remember this stuff, because they're a little bit weird. So the tangent, let me slide this up a bit, is a line, segment, ray that touches the circle at one spot and it's perpendicular to a radius. Okay. So your tangents you get that. And as we get into this, there's ways that I can kind of draw it better on the smartboard than I can on here, but you get kind of that idea. But if you look, if you squint, you tilt your head just right, the line where it touches the circle at one spot kind of makes a T. Stretching it here, but trying to think of some easy way to write this out. Okay. Trying to think of some easy way for you to write that out. So you could say, F, G is tangent to circle A at point H. That's what that would look like. Yes, sir. Yeah. That's what that would look like. And we're going to spend a lot of time on this whole tangent thing here because of that. And what have we been doing? Right triangle stuff. Because you can create right triangles all the time with this stuff. Okay? You get a lot of that. All right? Definition's okay? My suggestion, I will probably come up with a circle, like a big circle picture thing. There's a couple of them on there. You know how we did proof progressions before? No, don't freak. There's no proofs. I don't want you to think of that. Because you looked up right away and went, oh crap. No, don't worry. I'm not making you do proofs or anything, but with all these little definitions and diagrams and things like that, because there's a lot of them here. What I normally do, and I just haven't gotten to it yet today, is usually what I'll do is I make you know how we did the squares? What I'll do instead of squares, I'll make circles. And I'll do like 6 of them on a sheet. And that way you can you can draw a picture like this and say, hey, DE is a chord. That way you can visualize what everything is as you're going through it. And have that as you run it through with your homeworks and stuff like that. Is that? Yeah, but not squares, just circles. Could you put a square inside of a circle? Could you put a circle inside of a square?
No.
Yeah.
Sorry.
Yeah. It's called inscribed or circumscribed. You can do either way. There's a bunch of different things you can do. So, and we'll actually draw and do all that junk later on. Okay. Yeah, I'll get that to you. We'll do that tomorrow. So we'll start filling stuff in. So we got all this. We just did this. Another one. Don't worry about these names. I don't know why I left that in there. This is stupid. Don't ever write down weird numbers. if two tangents start at the same spot, and they touch the circle, from where they start to where they touch the circle, that distance has to be the same. It has to be. And there's reasons why. So this is called a common external tangent. It's basically you have two different rays. You have ray AB and ray AC. Those two, if you want to think about it, it's angle ABC. If you want to think of it that way. They have that common vertex at point A. If you take a circle and you place it inside that angle, that circle will be touched at two spots. Bless you. Those two spots would be the same distance to the vertex. You've actually did stuff like this before. When we had if you lied on the angle bisector, you were equidistant and perpendicular to the side. Remember that from chapter 7? Do you remember that vaguely? Because watch what happens here. What is this segment called from E to B? It's a radius. What is E to C? What do you know about all radius in a circle? They're all the same. Remember that? Did we not write that down? Radius are all, they're all congruent. They're all the same distance, okay? Radii are always the same inside of a circle. Okay. So if you draw this, you get that. Since they're tangent, they're perpendicular, so you get that right angle. Now, if I draw this, between those two triangles, what is that segment between A and E called? How do we say that it's congruent to itself? It's reflexive, very good. So if this technically becomes reflexive, right angle, hypotenuse, and a leg. You get hypotenuse leg. It all comes back to what you've done here before. This is the exact same thing, but we're just drawing a circle in it. It's the exact same property as an angle bisector from before. It's the same thing. What's different? We put a circle in the middle of it. Everything else is the same, okay? So as weird as this looks, and as odd as this sounds, you've done this. It's just got a different piece of a diagram to it, okay? That's all. Eh? What do you mean? Here's what I'm saying. I can say that these two triangles, this triangle ABE and ACE, those two triangles are congruent because of hypotenuse leg. So if their hypotenuse legs are congruent, then that means that CPCTC, the corresponding parts, that whole spiel, that means that these two distances are the same. And that's what it's getting at. The point from out here to the circle is always going to be the same because of the properties of things that you have done in the past. All that we're doing is just changing the picture. Okay? It's just changing the picture. So the algebra that we do here looks a whole heck of a lot like the algebra that you've seen before. It's just going to have a circle in the middle of it. That's about the only difference. All right? So let me show you an example. Oh, actually, you know what? Yeah, let's do this. Sorry, for some reason this got out of order here. Let me put this back up in order. I was looking at this morning. So these guys are all common external tangents. And we'll just do one of them. We'll do one of them at a time, or two of them.
All you're going to do is find x, right?
Yeah. So it'll tell you in directions here that JK and JM are common external tangents. By being a common external tangent, that means they start at the same point and they touch the circle at one spot. And it also means that those two segments have to be what? Equal. They have to be equal. So algebraically then, you have an algebra problem that you've all done. Okay? So by saying that these two guys are common external tangents, you know that that has to happen. So algebraically, you get 3x is x plus 12. So what do you do? Yes, sir.
I got x equals 6.
I agree. Subtract the x, you get 2x is 12, and x is 6. And what could you always do to see if you are correct? Substitute back in. 3 times 6. 6 plus 12. Da, da, da. Okay. Same deal on the other one. You've got two common external tangents. You write it out. What do you got, Kev?
X equals 2.
X equals 2? Well, my brain doesn't go that fast. Let me write this out. Subtract the 2x. Add the 4. 3x is.
6.
Therefore, x is. Good. I will tell you one thing. This stuff, a lot of times you might see x values that are going to be negative because they will throw that in there. But if you substitute in, you might get positive. So always, that's why I'm trying to get you guys back in the habit of double checking your answers, just to make sure you're not screwing up. So let's see. 5 times 2 is 10. Subtract 4 is 6. 2 times 2 is 4 plus 2 is 6. Yay, math. Okay. Sure. Oh, I got ahead of him. You will see a ton of factoring in this section. You will see a ton of factoring. Now, it does not say in this one that they are common external tangents, but what in the diagram gives it away that they are? The right triangle. Yeah, good. The right triangles. The right triangles do. Because those right triangles, those right angles are created from radii. The radii is the plural of radius. They're the same distance from the center. They're perpendicular. And those two segments, excuse me, and those two segments get to the same spot. That means they have to be equal. So you get this. You get 3x squared minus 10 has to equal. Now, is this going to be a straight factoring problem, or is this a solve for x problem? It's actually a solve for x problem, because since there's only an x squared term, there's no other x term that you have to worry about factoring. Okay. So what do you do first? Yeah, 10, good. Now what are you, Logan? You were about to answer me. No. Divide by 3. Yes. What happens here, guys, and this, I'm actually kind of glad you made that mistake, is that when you're solving equations, you're doing your order of operations backwards. Okay. So if you're solving equations, you're doing your when you're solving, you go backwards. So you work your way backwards. There's no subtraction. We did the addition. Then we have to worry about the division part. So you divide out by the 3. And now you get x squared is 9. What's the square root of 9? 4. Very good. Back to the point of the idea.
Always have 2 answers.
Yeah. What happens here a lot of times is that you get, whenever you take a square root over an equal sign, the main rule that you guys always had to follow was that your answers would be plus minus. Because it's asking you, what are 2 numbers that are the same number that you multiply together to get 9? 3 times 3, negative 3 times negative 3. Because, in this case, if I substitute in a negative 3, what's negative 3 squared? 9. What's 9 times 3? It's 27 minus 10. So it works. So there are 2 solutions to this. It's plus or minus 3. You guys remember how to put in a negative 3 in your calculator if you're going to square it, right? No.
What do you mean?
Put parentheses around it. If you don't put parentheses around it, you're going to be wrong. Okay. If you don't put parentheses around it, you're going to be wrong. Calculators aren't that smart, no matter what you may think. Negative 3 squared, what the calculator is doing, it's taking 3 squared and multiplying it by negative 1. That's what the calculator thinks what you're doing. It doesn't assume that it's the number negative 3 until you put that in parentheses. So if you're unsure of how to do something and you have negatives, always, 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 always group negatives with parentheses. That way you won't goof up. Okay? That's how we do on that one. Yes, sir. Yeah. Yes, we got.
Is it wrong if you take the square root as your number?
Yes. Because what'll happen is sometimes it works, but a lot of times it doesn't. For example, if I took the square root of 27, I get 3 root 3.
No, I mean, like square.
I thought you were taking, what do you mean?
Do 3 times 3.
Uh-huh, 9.
3 would be 9, 27.
What are you trying to do?
Okay, go back to the front. Instead of dividing the 3 first, I just multiply the 3 by 3.
For, just like here? Oh, you're just trying to figure, you just did it in your head?
Yeah.
That's fine, but you neglected the negative 3. I thought you were saying, like Logan was saying, well, hey, can I just take the square root here? That's why that won't work, we need to do it that way. Okay, that way, that doesn't work. Okay. Yeah, always, try to force yourself to always do everything you can by moving everything over till you get left with this, because then you do your, because that's the only time you can take the square root, is when you have nothing in front of the x. Okay.
Has to be a negative.
I'm sorry, what's that?
Has to be a negative number when you put it in the calculator.
What do you mean?
Like, do you have to be parentheses around it?
No, you don't. You
So
don't.
only a negative?
Yeah,
Okay.
yeah. Whenever you're squaring something, if the number is negative, make sure you throw it in parentheses. Also, if you ever have a square root symbol that you have got to square, and there's a number out in front of it, like 3 root 2, and you have to square that, you have to put parentheses around both things. The calculator doesn't want you better. Common tangents. Common tangents are tangents that can occur between 2 circles or more circles. So basically what happens is, how many ways can you draw a line or a segment or something like that that would touch both circles at just one spot? What's that? Many times, yeah. It's actually a lot easier than what it sounds like. But for the first example,
There's 2.
where?
Yeah.
Oh, okay. You're staying where they intersect each other. What I want you to do is draw a tangent, a common tangent that would touch both circles at just one spot.
Okay.
I got
Go help me.
Oh, I get it.
What's a tangent again?
Where it touches it in. Oh, wait. It could it be like right here?
No, because that goes through gold. Yeah, that's
Oh,
it.
okay.
See, once you saw it, yeah, that's how that would look. Okay. Now, what would you do for the second one?
So all these little problems right here, these are all tangents.
Yeah. You're saying the same thing? Okay. Those are what we call badly drawn. Those are called, when they're on the outside of circles, they're called external tangents. They touch on the outsides of circles. Then you can do more because you can go in between them. In this case, you can do this as well.
Sneaky.
Uh-huh. Sorry. I'm not really good at drawing. When they go, yeah, thanks. You're just figuring this out, ladies and gentlemen. I'm sorry to let you down, but you know, you'll get over it. What you don't see it very often. This is one of those things that I do know for a fact that I've seen on the actual ACT test. They will ask you questions like this: How many tangent segments can you draw in this diagram? Well, that one would be 4. What about the next one? 1. Just 1. Because these two circles only touch at one spot, so it'd just be one of them. Ooh, I actually did that one nicely.
Congrats.
Okay, here's a $1 million question for you. No. How many non-overlapping segments can you draw?
Sounds like the.
How many non-overlapping segments can you draw inside of a circle?
0.
A lot.
0.
Actually, you know what? I forgot how it's worded. I might be wording this wrong. I have to re-look it up because this is actually the ACT, one of the ACT questions from 3 years ago. I have it in a book here. I'll redo this question with you guys tomorrow. I think I'm wording it incorrectly. It's been a while since I've looked at it. So now what do you do?
Oh.
Very good.
Whatever.
Why? That's an X. It's a right triangle. How do you solve for X? Pythagorean theorem. It's just the good old-fashioned Pythagorean theorem that shows up quite often because that segment that's 96 would be a tangent, which creates the right angle to the radius, which is X, and that 100 then becomes the hypotenuse. Okay. So as I go through that, just like Justin just said, it's Pythagorean theorem.
And it'd be 10,000.
Yeah, a squared plus b squared equals c squared. So, now, have you guys done this yet without having to reword everything or rewrite everything or type everything in the calculator each step? Have you gotten to the point where you can just write x squared is going to equal 100 squared minus 96 squared and then just type this into your calculator? Can you guys do that yet? Hope so.
It doesn't really work.
So if I do that, I have 100 squared minus 96 squared, and I hit enter. That number equals x squared. What do I do to that number?
Take the square root.
Square root of it. So your calculator would do the same thing. Second square root of your, I get 28. So my radius is 28. Can I have, I took a square root of some number. Thank you. And I got x is equal to 28. I took a square root over an equal sign. I should write plus minus here, shouldn't I?
Yeah.
Can I have a negative radius though? No. Can you have a negative segment?
No.
No.
So then you wouldn't be able to.
Right. So there are times that you have to sit there and think, will the negative be okay or will the negative not be okay? It wouldn't be, because can you go a negative distance?
No.
Can you go a negative direction?
Yes.
You go, you go the wrong way, yeah. What happens here is that the radius value is always some specific distance. Distance will never be negative, okay? We got a lot more to do with this. Let me give you just a couple of these for today. So this is 10-1.
Iowa.
We'll keep going with this tomorrow. We'll just start with that, okay? We'll start with that. I know that the chapter 10 stuff is up and going. I will double check, make sure everything is resourceable, if you will, and go from there. But, gotta do the homework, guys.
That's a good idea.
Usually. I mean,
Helps you grade.
I'm,
You don't need to study. You don't even like check it to see if it's done.
I mean,
It's easy.
it's just practice stuff, man. That's all it is.